Hey friends, it's Alan. This is our first one. Wanted to make sure that I go a little bit slower so that you know what to expect. And if you do have questions, feel free to email, message me, let me know. Here we go with chapter 1, section 1.0. Not quite getting into the review of these functions yet, but more or less why we learned algebra and talking about some of the key concepts. So I will never sit here and read this to you. That's all on you guys to do. I will just fill in some key concepts that I want to make sure I emphasize by leaving them blank and or allowing you guys to derive some things with me or at least see them. So I will pose questions as if we were in the classroom, but go ahead and pause it at certain parts. Feel free to read through it, but I will never do that to you and I won't insult your intelligence. So we are going to get at why we learned algebra, because a lot of students always ask, when are we ever going to use this? So a few quick questions, if you guys would like to pause it real quick and read through them, and then we'll go over. All right, hopefully you're able to pause, read through those. What is the first thing that comes to mind when you think of algebra? Now, again, your answers may vary, it may be a little bit different, but we're going to talk about some of these and what I anticipate you guys coming up with. All right. And a lot of people think of algebra, they'll think a line or y equals mx plus b, variables, your x or x's or whatever it might be. Question number 2, what topic do you remember learning first in algebra? Yeah, lines. And those were some of the things that were the simplest. That's why we started with them. So those types of functions. So I'll just go ahead and put in here for number 2, lines. Number 3, what type of function was first discussed? Yep, hopefully you remember that would be the same type of thing. So you kind of get the theme that I'm going at here. What would you need at minimum in order to draw or graph a line? And then more importantly, why do we graph? Well, hopefully you answered 2 points at minimum. And why do we graph? Well, remember, these equations that we're talking about here actually compare one side to the other and say that they would be equivalent. Now, the M and the B stand for certain things. We'll get to that when we review, but hopefully you remember it's called slope intercept form. The X and the Y are actually the variables, the things that can vary or change. And so if this and this are some number, if we were to choose some X and multiply it by that M, add or subtract some B, then that would yield one and only one output we call the Y value. Now, if there's only 2 points, are those the only 2 things that work? Well, no, that's why we draw a line. It represents not just this point and this point, but when we connect those dots, every single point on here and everyone in between are also solutions to this line, which is why we draw arrows, because it actually goes indefinitely. But only those solutions along our X and Y axis, for example. Okay, so the last thing, what is the most critical component of these lines? Little thing we call slope. That M. All right, so these are the things that we started with in algebra, introducing these unknowns, these variables. We're going to get into even more detail with slope and lines as we progress through, but at a higher level we call calculus. So here are some follow-up questions. How do you find the slope of a line? Can the equation of slope be used to find anything else? And if so, what? And do you remember all the various ways to write the equation of a line? So go ahead and pause, think about that, see if you can come up with at least some of the answers that I anticipate you all getting, and I'll quickly go over it with you in a second. Go ahead and pause and reflect. All right. Question number 1, how do you answer it? How do you find the slope of a line? Difference in our y's over the difference in our x's. Now, you guys will learn very quickly that mathematicians, we're a bit, I don't want to say lazy, but we like to think smarter, not work harder. So we make up symbols for a lot of things. And the symbol we use for the difference, it's a Greek letter, delta. All right, it's like a lowercase d equivalent in the English language. All right, so delta y over delta x, which we could then say is if we have those 2 points, then those are called subscripts, not exponents, y2 minus y1 over x2 minus x1. Or if you wanted to say that there was some point which we got to as an x in it, bunch of different ways to write it that we will see down the road, and I'll leave the last version of this for that road. So these are all equivalent to what we call m, which is our slope. Question 2 asks, can it be used to find anything else, and if so, what? Well, hopefully you remember that we just came up with this is typically the one that we use for slope, and there is an alternative version that we will use of that as an adaptation to come up with a few different types, as we mentioned here, and then we'll add some on a little bit later. So what we are looking at with the slope is how one thing changes compared to another. Again, change in our y's over the change in our x's, right? It could be the change in our position over time, right? How many miles did we go in how many hours? Well, talk more about that and bridge that gap from algebra to calculus in a bit, all right? But before we do, last question here, question 3. Do you remember all the various ways to write the equation of a line? Well, obviously, we already went over the one that most remember, but there's also this, which we called standard form, and even one other that I want to derive with you called point slope form. So this one, most commonly used, slope intercept, because we are given the slope and the y-intercept. But what if we just took this, which is the equation for slope, and said instead of having 2 points, we only had 1, and we knew the slope. So if we were to have that, you can see that's a pretty gnarly equation because it's got a fraction in it, and we'd rather not work with those if we don't have to. So this right here means divide, and the way that we undo that is by multiplying. So we're going to go ahead and multiply both sides by the x2 minus x1 so that we know anything divided by itself becomes a 1. And so you can see on one side, we are left with the y2 minus y1. And on the other side, we have the slope times the x2 minus x1. So it looks a little bit better because now there's no fraction like we had in the original here in green. But as I mentioned before, what if we didn't have 2 points? We actually just knew 1 point, x1, y1, and the slope. Well, then all we have to do basically is get rid of that second point. And then you can see this new form, which is called point slope. I have my 1 point and I have my slope. Notice it's a y equals x form again, just like this one and this one, where the m and the b are known values and the a, b, and c here are known values. Positive, negative, whole numbers, fractions, whatever. Okay? So again, just a quick review on lines, something that we will actually use quite frequently and talk about at the beginning here a lot. Here's my next question. Would you be impressed if I told you I rode my bike to work? You're like, no, you're probably still working from home. No. If I went into the college, would you be impressed if I rode my bike to work? And why or why not? If you want to pause and ponder these questions real quick, go for it. I'd be impressed if you did. And if not, let's talk through this. Would you be impressed? And if not, what other information would you like to know in order to be? Well, what if I told you I did and I live 20 miles away? Now would you be impressed? Well, what if I told you I left yesterday? Well, you may not be as impressed anymore. You need to know not only the distance, you also want to know the time that it took. And so let's just make the numbers easy. Let's say it took me 2 hours to ride those 20 miles. Well, what do you think that you could figure out now that you know how far I live away? Well, let's say we took this as a start and end scenario where I started at my house and I rode to work. Now, again, I'm not saying it's in a straight line. It's not a helicopter. It's a bicycle. So yeah, I'll probably have to go some different routes, but let's call this 0.00. where my time and my distance are at 0. Well, the work would be what? 2 hours it took me to ride those 20 miles. So as you can see, we can find the slope, like we just mentioned, between those two things, one changing compared to another. And let's go ahead and take the distance over the time. And let's say that we are dealing with some starting and ending point. And if we did that to find that slope, it would be our y2 minus y1 over x2 minus x1. And for this scenario, we would have finding the difference. On top, we get 20 miles. Bottom, we get 2 hours. Again, just trying to make the numbers easy. But notice what I ended up with. Of course, a fraction, but we always like to simplify if we can. So 2 goes in that 10. So we get 10 miles per every 1 hour. And if you heard how I said that, as I wrote the division bar, I actually said per hour, which we also like to abbreviate as 10 miles per hour. Notice what we came up with was the slope. But what does this represent? What would you call that? That, my friends, we call a rate, a speed, miles per hour. Now, does that mean that as soon as I got on my bike, I was going 10 miles an hour and then I went all the way to work? Well, no, this is actually going to represent my average rate that I traveled, okay? So these are the things that we're going to explore with the basic algebra concepts like lines, like a slope between 2 points. And we're going to look at what else we can use it for, like an average rate of speed, okay? Or change, we call it. So let's take a quick look at a more generic version without having values, and let's see what we can discover. How would I get to this first point here and that second point? Well, I'd have to go over some x, and then I'd have to go up some y. How far is that x and that y? Well, I don't know, and that's why I didn't label my axes. We'll just call them x1 and y1, which means how far over would we have to travel here? Well, that would be some second x, and to get over there, some second y. So to label these things, it would look a little something like that, where we could actually label this point here, this first one, as x1, y1, and this point, x2, y2. So what we can actually find, again, is the slope of these things, which would just be, but what if I didn't just want to find how much I rose and ran, whether it was that way or this way? What if I wanted to find the distance between those 2 points? How would I find that length? And we could find this distance horizontally and that distance vertically. And if you notice, we didn't just create any old triangle. It would therefore be a right triangle. And what would that distance from here to here be? And there to there? Well, that's why we take the bigger values typically and subtract so that we get positive values. So to find that distance from here to here, that would be a x2 minus x1. And from here to here, y2 minus y1. And if you remember from trig, if we know 2 out of our 3 sides of a right triangle, what can we use to find the third? In this case, the hypotenuse, the Pythagorean theorem. And so what we are going to do to find this distance, I will call d, is we will take the hypotenuse squared and set it equal to the 2 legs of that triangle squared. Now, don't forget what we're trying to actually find is what d is, that distance there, not d squared. So we would have to do one last step, and that would be to take the square root of both sides of my equation. And by doing that, I found d. Unfortunately, though, this is what's left on the other side. And that, my friends, is the distance formula for 2 points. We just derived it. So whether we write our slope like this, or we call it something different like this, we could call each of these things, instead of x1 and x2, we could say this is any value, and this is any other value. call it x, since we're along the x-axis. And to get to those values, we would have to just simply plug this into our lines function, which we can go ahead and name that as well, y equals f of x, for example. And we can just use the same thing but different letters. To find that y value height, we would just plug it in to see what comes out. And so we would get the bigger value further to the right of our x-axis, and we would get our slope to be. So that is a different version of this. And there's even a third that I want to mention. Instead of calling it some random letter, let's keep it uniform like we did with the x1 and x2, but instead of calling them two different x's, let's just name this gap between them. Okay, so very similar to the stuff that we just did, but let's take it one step further to make it look even a bit different. And let's say instead of this being there, let's call that a gap of h. Heck if I know how far apart these are, but let's call it a distance of h. So then if this is a value of x, then this from x to here would add that distance of h. So then we could say that this is x plus h. And if we did something similar to this one here, where we used the bigger one first and then the smaller one second, our top would look like this. But why is this going to be any better than the other ones? This looks simpler than that, but we won't always have just 2 points. We might have to find those y values. So that's why that one is sometimes used. Well, then why are we going to go and make it even uglier looking? Well, check out what actually happens on bottom. It's pretty nice. If you have an x plus h and you subtract an x, well, then the x's actually canceled out when you subtract them, and we are left with a new form where we only have an h on bottom. Some of you guys may recognize this. It is actually given a name. It's called the difference quotient, because that is exactly what we are doing, is finding the difference and dividing between two known values. But these are the types of things that we will be utilizing, not so much the distance formula, but more so these different forms of slope. And that's what this class is all about, is how can we use all of that algebra that we've learned in the past to discover new things. As a recap, I wanted to make sure what types of equations you remember, and we will list them one more time, and then we will make sure that we practice this stuff before we go on. So those are the equations for a line. Now we want to make sure that we know the names so that we can refer to them. So the first one there is called slope intercept. And remember, it's the y-intercept because that's what we are given it's equal to. So slope intercept. The next one, pretty standard, just has the x and the y on the same side with the coefficients a, b, and c as our constants. We call it standard form. And then the last one here, the one that we will use the most, is called point slope form. Those are the things that we may know, and this is going to be the thing that's a bit different in calculus compared to what we've seen in the past. So we already talked about where they came from. We derived those. Make sure that you remember this came from the slope formula. That's it. Short and sweet. Make sure that you remember how to do all of this. If not, go back, review, and then you guys can get started on practicing. So we will use these mostly the point slope form, but you can also use slope intercept form. Notice they are both equations for lines. All right. The only other thing that we want to talk about with lines is those special scenarios when we have multiple lines. And so what does happen sometimes with multiple lines graphed on the same grid? Well, they could be parallel. They could intersect in no special way, or they can intersect in a way that creates not just a right angle, but technically there's 4 right angles, a square. Right? And if we just took something like that and turned it a bit, you can see that we would end up with our X and Y axis. Right? So remember, what does it mean to be parallel? If this is line 1 and this is line 2, then that means the slope of line 1 is equivalent to the slope of line 2. What does it mean if, turn these back here, line 1 and line 2 are perpendicular? Well, as you can see, one of them is going to have positive slope from left to right. It's increasing. And from left to right, the other is decreasing. So what are their slopes? One of them is going to have to be positive, and the other is going to have to be negative. But is that it? Or is there any other special circumstance that makes these exactly 90 degrees? Positive and negative for sure, but they also have to be reciprocals. So remember, perpendicular lines are both opposites and reciprocal slopes, where if they are parallel, same slopes. And it's pretty easy to see the parallel. That's just like our equal sign for the same, equivalent. All right, parallel, same slopes. Opposite and reciprocal. Make sure that you know that because one's going to be positive, one's going to be negative, that they have opposite signs. All right, so we have a slope 1 would be perpendicular if it was the opposite and flipped. So for example, if slope 1 had positive a over b, to be perpendicular, slope 2 would have to be negative b over a. All right, so these are the things that basic algebra, and I know you're like, calculus, all right, this is easy. We'll get there. We'll get there, but we're starting with the basics, so make sure you have this down. Remember, first chapter is all review. If you have any questions, let me know. Reach out to our TA, any of your classmates, and keep working hard. All I have now for you are a few examples, or what I like to call drills. All right, you can do as many of these as you need to. I have a few for you set up already. Pretty standard stuff. Just getting you used to the first part of algebra that we learned to make sure that we can then apply this to a more advanced calculus level. Until the next time.